Hello, this is Dr. Mode, and welcome to ICP today. Our lesson is still in the chapter on energy sources, and today we're going to start the section on nuclear energy. Our scripture verse for today is from Matthew chapter 7, verse 12. It says, "So whatever you wish that others would do to you, do also to them, for this is the law and the prophets." So in Chapter 8 so far, we have finished Section 1 on fossil fuels, and we are starting Section 2 on nuclear energy. Fusion. Our sun is an enormous nuclear reactor, and fusion occurs when atomic nuclei combine at very high temperatures, and this typically involves small nuclei like hydrogen and helium and so on. A small amount of mass is converted into a huge amount of thermal energy. Now, fusion power plants are not practical. They require energy to heat to millions of degrees to get the fusion process going and continuing. That also causes a containment issue because you would have to contain this substance that is heated to that temperature. So for these reasons, it is not a practical power source. Now, fission is different. Fission occurs when atoms are split apart and release energy. So these atoms are typically larger atoms. So again, a small amount of mass is converted to a huge amount of thermal energy, just like in fusion. Fission power plants are practical. The United States has 65 fission plants, and they provide about 8% of the U.S. energy needs. Nuclear reactors. They use energy from controlled nuclear reactions to make electricity. They have control rods, a fissionable fuel, and a cooling system. In the picture here, you can see that the largest object is a cooling tower, and because it generates so much heat, the water that's used to cool it has to be cooled back down, and they flow round and round these cooling towers to do so. Now, only certain isotopes can undergo fission. Uranium is used as one of the nuclear fuels. Uranium-235 is the isotope that's required for this reaction. And of all the uranium, it accounts for less than 1% of it. So enrichment of that isotope is required. So the nuclear fuel is formed into these little pellets that are a little bit larger than pencil erasers, and they're stacked together to form fuel rods. These fuel rods are then bundled together to form these fuel bundles. A typical reactor contains about 100,000 kilograms of uranium, and for every 1 kilogram of uranium that undergoes fission, about 1 gram is converted into energy. This form of nuclear energy can be very dangerous, and that's why it is used for nuclear bombs. But since we don't want our power plants to blow up, we have to be very careful about that. So what happens is you have a uranium-235 isotope that's hit with a neutron, and that neutron splits that isotope into 2 smaller nuclei, and 2 to 3 free neutrons are also produced. And you can see that we started with 1 neutron, and now we have 2 to 3 more that are used to continue this reaction. They go and hit more uranium. Well, because this continues to multiply bigger and bigger, it doesn't take very many steps before this can quickly get out of control. So control rods containing maybe boron or cadmium are used to absorb some of those neutrons to prevent the reaction from running away and going way too fast.